Hello, legends. This is Mr. Maze coming to you through the digital universe. And today we're going to be going through our 5.2 notes. And specifically, of course, because numbering notes only gets us so far, what we're going to be studying today is specifically sampling distributions, but not just generally like we did last time. This time we're going to be looking specifically at how they relate to proportions. Now, as you remember, from our last class of notes, there are sampling distributions for means, right? And there are sampling distributions for proportions. And sampling distributions for means, for the most part, we use for quantitative data. And I actually should say, if I can spell right, not even for the most part. We always are using means for quantitative data, right? It makes good sense. You take a bunch of values, you average them out, and that average would be the sort of center that we produce. On the other hand, with proportions, we do find a mean proportion, but we are interested in specifically the proportions. So the value over the total. And the total here would be the n, number of people in your sample, right? So a couple things I really want to hammer home, because we're specifically talking about these bad boys today. And as we might remember from last lesson, proportions are specific to categorical data, right? We don't want we can't get a bunch of numbers and specifically mean them where each one of those numbers represents something determinate, right? Like your height or your weight or something like that. So instead, what we do is we look at the number of people that say yes to something or that agree with something or that are willing to make a certain statement over the total number of people we interview. And so what we do effectively is we take categorical ideas and turn them into numbers, and those numbers are called proportions. Always a decimal. In the end, all of them adding up to one whole. So quick side note, at the end of last lesson, we talked about biased versus unbiased and variable versus high variability versus low variability. I want to look at bias and unbiased for a second. And I specifically want to look at some shapes that are considered unbiased for the mean. Remember that unbiased and biased relates directly to whatever your parameter of interest is. And for the most part in statistics, at least in our AP statistics class, that parameter is going to be the mean. Either it's going to be just the mean, right, like it is for any quantitative data, or the parameter is going to be the mean of the sample proportions, right? So if you remember from last class, p hat represents the proportion that you get in a single sample of n people, whatever that is. And then when you arrange a bunch of those samples together onto a distribution, we then have a sampling distribution of proportions, which is what we're going into more detail on today. And with that in mind, we take the mean of the proportions, which is different than taking a mean in general. This is taking the mean of all of the proportions we got. And that gives us what we treat as our true population proportion, right? What we view to be the pie in the sky real number of people. So the following shapes are unbiased for mean if the mean equals 0. So let's say our mean is 0, and I'm going to show you these 4 graphs. And if you're taking a look at the slideshow alongside this is on slide 6, right? These are my 4 little graphs. One of them is an approximately normal curve, where 0 is right in the middle. Then to the right of that, we have one that's a fairly uniform distribution. There's some ups and downs. But again, 0 right about down the middle. The third one is a bimodal distribution. 0 right down the middle. And the fourth one is a right skewed distribution, with the 0 sitting right in the middle of all of the data, despite the skew. All 4 of these would be considered unbiased for the mean of 0. And the reason why is bias has to do with how accurate your result is. Does your total calculation for the entire distribution come close to the expected value we would have, right? The population proportion or the population mean that we expect. And so all of these would average out to 0 as a mean, making them all unbiased. On the other hand, right, if we do have something like, if you turn to slide 7 and slide 8, you'll see that, like, for example, A, C, and D are all unbiased, but statistic B, that's pretty biased. And the reason why is, even though it's normally distributed for the most part, the mean would sit somewhere in the 60s, not at 50, and we asked for a parameter of 50 in that particular question. So something I really wanted to hammer home is, on the AP exam, they often look for the parameter of mean or population proportion mean, right? And if that's the case, and they say something about, is it biased or unbiased, weird shapes can still be unbiased as long as they mean out or average out to the correct parameter that we're looking for. Now, the important question, of course, all known, is, well, which one of these is the best estimator? And of course, the answer would be this first one would be the best estimator, because the majority of my data sits at where the mean ought to be, and that's what we're looking for. Similarly, for question for the question on slide 8, statistic A would be the best one because it is fairly normally distributed, but it is also fairly normally distributed over the parameter of interest. Okay, hopefully that makes some good sense. We're going to keep rocking and rolling forward. Okay, we are on slide 9, and here we're just talking about how we create a sampling distribution. Let me sketch it out for you. If we do this, and I kind of brought this up a second ago, let's imagine that this black dot is equal to a sample, a single sample that I do, right? That sample is going to have a p-hat, and that p-hat is basically the proportion of people that said yes or no to something in that sample, or that agreed to something in that sample, whatever it is. So I'm going to use the example of, let's say, let's be self-flattering, proportion of kids in my class who think I am a dope teacher, right? Let's say it's a horrific 0.1. Only 10% of you. Guys, I'm never going to recover if you keep throwing, like you're going right for the jugular. Let's say that I do that in one sample, one class, right? And let's say that class is around 30 kids, because that's about the average number of kids I have in a class, okay? So that would mean n equals 30. And that would mean my p-hat equals 0.1. Again, p-hat being the notation we learned last class for the proportion of a single sample. Well, what I would do then is I would set up, 0, 0.1, 0.2, 0.3, 0.4, and so on, going down. And then over each one of those, this of course would be my frequency on my y-axis. Oh, goodness me. I almost wrote frequency. Who am I? I'm Spider-Man. Thank you. Frequency. Okay, so for proportion of 0.1, we have one dot. All that a sampling distribution for proportion is, you do a bunch of these. You do many samples, and the key here, and this language is important, it should be in your notes, many samples of size, and then you say it, n equals, in this case, 30. Change this, of course, to whatever n is, right? Of size n equals blah. They have to be of the same size, okay? And then we plot them. So let's say another class gave me a 0.2, another class a 0.4, and then I did another couple and another one gave me 0.2, right? And I do them over and over and over again, okay? And I start to get a curve that is functional for me, right? And what we're trying to estimate with this sampling distribution is the parameter P, the true population proportion, okay? And the way we get that is and I said this earlier, find the mean of all of our p-hats. So I would add, 0.1 plus 0.1 plus 0.1 plus 0.2 plus 0.2 plus 0.2 plus 0.2 plus 0.3 plus 0.3 plus 0.3 plus 0.3 plus 0.4 plus 0.4, and I would average them together, and that would give me my mean for the sampling distribution. And we treat that like the true population proportion until we either disprove it or find better research, okay? Remember, of course, that if the sampling method is unbiased, the mean of the sampling distribution, right, mean of p-hat, will be equal to the true population proportion. So that's our goal. We take an unbiased set of samples, and lo and behold, we get what we want. If they are biased, we're in trouble. Again, if I were to be like, this affects your grade, is Mr. Mays the dopest teacher? I'm going to get much higher results. And therefore, it's not going to be accurate because it's not going to be biased, or because it's going to be biased toward higher proportions, despite the fact that my actual population mean is somewhere in the 0.2 to 0.3 range. Okay, hopefully that makes good sense to you. Moving on to slide 10, we have two very important equations here that you need to know. But of course, they are provided for you on the AP exam because that's awesome. Already said it, mean of the population is going to be, or population proportion is going to be treated as the true population proportion, right? The pie in the sky value. The standard deviation, which of course is very important, of our sample distribution is equal to the true population proportion times 1 minus the true population proportion divided by n square rooted. So that would mean that the variance for this distribution is equal to probability of success, whatever that is, in this case, me being a dope teacher, times the probability of failure, me not being a dope teacher, divided by the total number of people in the sample. Very key here. This n is number in my samples, not the number of samples. So if I go up here, n is 30. It is not 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. It's not the number of samples in my true population proportion mean determination. It is the number of people in my samples, the number of subjects in my samples. And there's an important reason for that. And that's that when we replicate a study over and over and over and over again, the number of people that we use for that study is the key factor here. We are recreating groups of 30 and checking this, right? If I did this over and over again with a group of 1, I would only be available to have a 1.0 or a 0.0 determinate value for my proportions, and that affects my sample. So sample size is always going to be the important n here. Okay, you're going to need to know these equations and how to use them effectively. Be able to know that these are what we use specifically for sampling distributions of proportions. Now, this is where I get to tell you some cool stuff. We're going to skip past slide 11, but you can use slide 11 to do sampling distributions for Reese's Pieces, specifically the number of orange Reese's Pieces. But on slide 12, we get a very important revelation, which is, you might have noticed a moment ago, I found a mean and a standard deviation for this. Now, you might be wondering, is there a sampling proportions CDF or PDF? Is that what this is leading us toward? Because we did this with binomial CDF and PDF, and we did this with geometric CDF and PDF, but we also did this with norm CDF. And what I want you to be aware of is, obviously, the second we have a mean and a standard deviation, we're going to find ways to find values under the curve. But, and this is the best part, sampling distributions for proportions, as long as your n is high enough, as long as your sample size is big enough, we can treat them as normal. And there's an easy 2-part test that we do to make sure we can do this. What we do is we take our number, n, we multiply it by the probability of success, whatever that is, and then we take n and multiply it by the probability of failure, whatever that is. And as long as those values are greater than or equal to the value of 10, as long as both that probability of success and that probability of failure are greater than 10, when multiplied or weighed by our sample size, we can treat it as normal. Which means we can use norm CDF. Love it. Beautiful. And that is a gorgeous thing. Okay, so for my sample, here's what I had. I had a sample of 30 kids that I checked with in each one of my sample sizes. And my true proportion was in the, let's say, 0.25. Right, that was my mean population proportion. So that, AKA this, if you will, using all our notations. So what do? We do our check. We do n times p, which would be in this case 30 times 0.25. And then I would do n times 1 minus p, which is 1 minus 0.25, which we all know would be 0.75. Okay. We run our calculations. We say to ourselves, what do we get? And of course, for 30 times 0.25, I am getting 7.5. And then for 30 times 0.75, right, I am getting 22.5. Okay. Now, and this is the key element here. We're good to go on our failure, right? 22.5 is good. We are not good to go on our success rate, right? 7.5 is less than 10. whereas 22.5 is greater than or equal to 10. So this one's good and this one is terrible. Therefore, we cannot treat it as normal. If, however, these two conditions are met, we can treat it as normal. They will almost always be met, right? But you have to check them and say it is approximately normal because this works. Okay. As you can see, going through the rest of the slides, these are a bunch of practice problems that you should use to make sure you fully understand these questions and that you can dissect the different question types, because you know AP loves to throw a weird question your way, okay? The last thing I need you to know, and this is gone over on slide 20, this is a side note, is that if sample size increases by n amount, whatever that is. So let's say some amount plus 5. Standard deviation will decrease by the square root of n, which is to say, really, if sample size goes up by some number, variance goes down by that number, right? If you think about it, what that's also saying is if n goes up by like 5, variance will go down by 5. And really, this is one of the best ways to understand what variance and therefore what standard deviation are. As your sample size increases by a certain amount, your variance, right, will go down by that amount. Because the more people you have, the more you can trust your results to condense down into a low variability curve, right? As n goes up, variability goes down, and therefore variance goes down. All right, you are legends, you are heroes. I am so proud of you. Go through these notes, know them inside out and backwards. This has been sampling distributions with proportions. Ask me questions, shoot me remind messages. Know that I am here for you. I love that I get to teach you. It is an honor and a privilege. This is Mr. Mays, signing off.